Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at Module 2, Module 3, Inquiry Question 2, Predicting Reactions of Metals. We're going to be investigating the following reactivities of metals with the following types of reaction: water, dilute acid, and oxygen. We'll look at metal ions in another lesson. So in our lesson today, we're going to identify different types of reactions that can occur with metals, and we're going to try and construct balanced chemical equations to reflect these types of reactions. Now, before we get into that, we should firstly revise on a concept known as ionic compounds. What will happen in most reactions between metals and the following types of reactions that we're going to discuss will form particular types of ionic compounds. So it's good to sort of revise on what they are. Firstly, you should remember ionic compound occurs when a cation reacts with an anion. Now, the best way to remember how to work out the charge numbers of each element is to look at where they are on the periodic table, specifically speaking, the group number. So it goes from group 1 to 18, but on group 13, we can also count it as group number 3 in the way we count ions. So group 1, we have sodium, that's +1. Group 2, magnesium is 2+. Group 3, which is aluminium, is 3+. Okay. As a way of remembering it a little bit easier, you can look at your periodic table of the different group numbers. Remember, it can go from 1 to 8 or 1 to 18. So, when it comes to working out the formula for the ionic compound, you need to firstly find what group number each of these atoms are, and then you label them out when you write them out. In this one here, we have the ionic compound calcium phosphide. Calcium is in group 2, so it has 2+. Phosphorus is in group number 5, and it has a charge number of 3-. If you come across a scenario where the charge numbers are different to each other, you must do the crisscross method, where you essentially exchange the number from one ion to the other as the new subscript. Now you can see that the negative and positive signs are taken out, because what we expect is the net charge of this compound will equal to 0. So if we check this idea out, the net charge of calcium phosphide should equal to 0. Now what we have here is calcium has a charge number, as we said, of 2+. There are 3 atoms of it, as seen here. And phosphorus has a charge of 3-, and there are 2 atoms of it. If we add them together, we have +6 added on with -6, or subtracted by 6. That equals to 0. And therefore, that is how an ionic compound works. Okay, next question we have here is just a nice little recap on writing the chemical formulas of a variety of ionic compounds. So this, you will need your periodic table. So if you would like to pause here, by all means go through. I'm going to go through all 24 of them, so we can do it like that. Okay. So we need to firstly know what each symbol represents and the charge number. So the charge number of potassium is +1 and oxygen is 2-. The formula to express, or the symbol to express potassium is K, and the formula to express oxygen is O, KO. As we know, this is +1, this is 2-. So in the crisscross method, K will have the subscript 2 and O would have the subscript 1. Now, because 1 is redundant, we don't need to put it down. Sodium is +1, sulfide is 2-, So we get Na2S, same as what we got up here. Ammonium chloride, chloride is 1 minus. If we look at the polyatomic ions chart over here, ammonia or ammonium is NH4 plus 1. So if we have a scenario where the charge numbers are equal but opposite, we just put the symbols together. So it's NH4Cl, as simple as that. The next stage we have is the calcium nitrate. So calcium is 2 plus, nitrate is 1 minus, and that is the symbol for nitrate there. So it'd be Na bracket NO3 bracket 2. The bracket is there because it's to represent that we have 2 nitrate ions that are present. Iron 2 represents it's 2 plus. Bromide means it's 1 minus. So FeBr2. Chromium 3 means it's 3 plus. Hydroxide is 1 minus. If you want to know, it's given by this equation here. So chromium is Cr bracket OH bracket 3. Remember, the bracket is to represent we have 3 ions of hydroxide. Copper 2, sulfate, which is 2 minus. This one over here. CuSO4, there we go. Aluminium is 3 plus, iodine is 1 minus. So I3, ammonium carbonate plus 1, 2 minus. So ammonium would be NH4 to CO3. Carbonate is given over here. Lithium bisulfate. So bisulfate is over on this side here. It's -1. Lithium is +1. So here we go. That's how you do that from there. Okay, manganese 3 plus with oxide, which is 2 minus. So manganese is Mn and oxide is obviously O. The 3 comes down as the subscript of O, and Mn has a subscript of 2. We have tin, which is 4 plus. Chlorate, which is 1 minus. So tin is Sn. Chlorate is ClO3. So we'll do the brackets and we write 4 at the bottom there. So hopefully that gives you sort of an idea of how to do these. I'm going to speed through 13 all the way to 24 now. So 2 plus bicarbonate is 1 minus. So it's MgHCO3 2. Zinc is 2 plus, that's 1 minus. So HO bracket 2. Potassium is +1. Phosphate is 3 minus. So it's 3PO4, that's phosphate. Acetate, that's here. So our formula here. Aluminium is 3 plus, acetate is 1 minus. So it'll be Al bracket C2H3O2 3. Mercury chloride, so mercury is HgCl2. Strontium is 2 plus. Sulfate is 2 minus. Strontium is a transition metal. If it's not told, you assume it's 2. So SrSO4. Silver is +1. That's what we know. So it's Ag2. Iron 2. Phosphate. So phosphate is 3 minus. So there's that. Calcium nitride So calcium is +2. Nitride, that's not given to you, but nitride is 3 minus. So it's Ca3N2. Lead 4 plus, and oxide 2 minus. So the Pb, you can write as 2, and then you can write oxide as 4. So that's one way. But the simplified version of this would be, we just take this away, would be PbO2. Copper 1, carbonate 2, so it'd be Cu2CO3. Ammonium, which is NH4 plus 1. Acetate, which is CH or C2H3O2. Okay, and that's how you would do these ones here. Okay, back on topic. We'll look at firstly what properties are there about metals, and we'll look at the applications. Firstly, metals are malleable, so you can hammer it or compress it into a particular shape without it cracking. They are ductile, so they can be made into really thin sheets, and they're good conductors of heat and electricity. So one of the applications is radiation shields. It's really good at reflecting infrared or UV radiation, and it's non-reactive with oxygen. So it's used as radiation shields for satellites and obviously for medical imagery. Another application is galvanization. So we actually use non-reactive metals to coat metals that could easily rust. So in the case of car, we can use zinc to coat a iron structure. The first reaction we're going to look into is metal and oxygen reaction. Okay, so that's this one down here. There's two types, as you can see. One over here is rusting, and over here we have combustion. So when it comes to metals reacting with oxygen, we'll form a metal oxide, but there are different types. The first type is a combustion reaction where oxygen is creating or making heat. Thermal energy has been added, and this is a really quick process, that, as you can see there. A second type of reaction with oxygen is through rusting. There is no added energy, and it's a really slow reaction. As you can see, the transformation that takes over days to occur, while as for combustion, it takes really a very short period of time. If we want to see metal-oxygen reaction, we can see it in the rusting of cars if the paint goes off. We can also see from the Statue of Liberty, the original color was, I think, copper, and over time it's reacted to become copper oxide, so there's that. Now this image that we have here is aeroplanes, I think in maybe Chicago, somewhere nice and dry. They actually park their airplanes outside. The reason being is in order for rusting to occur, it needs to be a high saturation of moisture, which in this case, because the Statue of Liberty is right next to the river, it is quite high there, but there's the difference there. So a couple of patterns you might need to take note of. Firstly, when a metal reacts with oxygen, it will form a metal oxide. So there are different categories. We have the really reactive metals, such as sodium or magnesium. These are from group 1. So these are group 1 and 2 metals. They are very reactive with oxygen. If we're looking at some transition metals like iron or group 3 type metals like aluminium, they would only be reactive if they're in their powder form. So it's still solid, but you need to grind it down to have a greater surface area. And then obviously silver and gold are non-reactive with oxygen. So hence why, silver and gold are generally used for jewelry or maybe sometimes cutlery as well because of the non-reactive nature of these metals. The next reaction we're going to look at is metal and water. So we have potassium water, lithium water, all from group 1, this one here. So the thing is, same idea as before, for highly reactive metals, say for example those from group 1 and also some from group 2, forms water, and we get metal oxide plus hydrogen gas. Same idea is true for the less reactive metals. Instead of using liquid water, we are using steam or water as a gas, and we form the same reaction here. So just keep note, for the reactive metals, we again have the group 1 or 2. Group 1 obviously the most reactive. We'll talk about why that's the case in our next lesson. And then for the less reactive metals, we need to use steam. Just take note of the difference in the labeling of the state of matter used. Okay, one's the gas form, one is the liquid form that we're going to use. Okay, we'll go into our first set of questions for this lesson, and that is to construct the word equations for the following reactions. Sodium plus oxygen, that would give us sodium oxide. Copper plus oxygen, that would give us copper oxide. If you want to give yourself a challenge, write the full balanced chemical equation for that particular reaction. Go down here, potassium plus water would give us potassium hydroxide and hydrogen gas. If I want to write down the equation, which I'll do shortly, I will do so. Okay, just to give myself a bit more space. And then we have calcium plus water. That will give us calcium hydroxide and hydrogen gas. In this case, we'll just shorthand and write it as hydrogen. Over here, we have aluminium and steam. That gives us aluminium hydroxide and hydrogen. So the same thing again. Okay, so potassium is K. S, might need another color. Okay, that's a bit better. Potassium plus H2O as a liquid gives us potassium hydroxide. That is aqueous because it's dissolved in water, and hydrogen gas, so H2 gas. If we have a look, we have an imbalance of the number of hydrogens. So let's make this into a nice even number of 2. So now I need to balance it here too, and I need to balance a 2 here. So that's done. Calcium, solid, plus water liquid, Ca bracket O2 plus H2. In this case, we have 4 hydrogens and 2 oxygens on this side, so we'll put a 2 here. Okay, and then the last one we have is aluminium. So to do the aluminium solid plus steam, which is H2O, steam, gas, aluminium OH3, whoops, get that sneaked in, and H2. In this case here, okay, what we can do, put the aluminium oxide, sorry, so it's oxide. Okay, I'll just do a quick correction here. If we have a if we have a metal that reacts with steam, doesn't form a metal hydroxide, it actually forms an oxide or metal hydroxide forms an oxide. So aluminium oxide plus hydrogen. Okay, so if I just rewrite that, it's Al solid plus H2O gas forms Al2O3 aqueous. This is solid. It comes out as a solid plus H2 as a gas. Okay, so a slight correction from what I said just then. Just take note that a solid forms metal oxide and a gas still. So slight difference between the two. Just make sure you get that. And while we're at it, probably make sure you copy this one down here. Okay, is the equation balanced? No, it is not. We have 2 aluminium, so we'll put a 2 here. Okay, and if we have a look, we have 3 oxygens here. So we'll put a 3 here. So that means we have 6 hydrogens. We can do it also 3 here. And that completes the question. Okay, when it comes to reaction with metals, sometimes with water or sometimes with an acid, hydrogen gas does get produced. And the way we can actually test if hydrogen gas has been produced, we do what we call the pop test. So what you can see here with the pop test, we essentially do a combustion reaction between the hydrogen gas and oxygen to produce water. So in the reaction, or the question we have here, to test that gas produced as hydrogen, you can collect the gas and carry out the pop test. So using the diagram on the right, describe what happens during the pop test. Well, what we actually try and do is perform a combustion reaction of hydrogen gas. With oxygen. Write a word and chemical equation for the chemical reaction of the pop test. That's given to you here. The other product formed from the reaction between metal and water is a metal hydroxide. Metal hydroxides are basic compounds, so just how could they be tested? So if we have a basic compound, we could use pH to test. And if we don't have the pH probe to test, we can also use universal indicator. So that's what we have. Just remember what the type of colors you get for base compounds. So for bases, it's generally from blue, or mostly blue, or blue-green to purple. So that's what we have. Okay, the last reaction we have is metal and dilute acid. So this one here, we're not going to do with the other metal ion solutions. So let's have a look. If we are dealing with a reactive metal, and by now you should still remember it is either group 1 or group 2 acids, we form a metal salt, hydrogen gas, and heat. It's just to demonstrate that it is an exothermic reaction. If we look at the states of matter, the metal is solid, the acid is aqueous, the metal salt formed is aqueous, hydrogen gas is a gas, obviously, by the name. If we're dealing with a less reactive metal, then additional heat might need to be used. So for example, the reaction between lead and hydrochloric acid, we might need to heat up the hydrochloric acid first. It doesn't need to be super hot. It could just be at 30, 40 degrees, a bit warmer. And that would cause the reaction to occur to make lead chloride and hydrogen gas. Okay, so this should be the final set of question for this video. It says, write the word equation for the chemicals formed. Well, a reaction between calcium and hydrochloric acid would form a metal salt. In this case, we have calcium. The non-metal in the acid would be chloride, so calcium chloride plus hydrogen. We're not going to bother writing gas because we know hydrogen gas is formed and it is diatomic. Zinc nitric acid, so it would be zinc nitrate plus, again, hydrogen gas. Lithium plus sulfuric acid, it would be lithium sulfate, and that also makes hydrogen. If we want to write that equation out, Ca solid plus HCl aqueous leads to calcium chloride, which is Aq plus H2G. Okay, let's just check if it's balanced. I have 2 chlorides here, 2 hydrogens here, and I only have 1 of each on the left-hand side. So I'll put a 2 here, and it's balanced. We have zinc, which is a solid, nitric acid, HNO3 aqueous. That leads us to have zinc nitrate. Now zinc has a charge number of 2, so it's 2 here, plus H2 here. Okay, so if I have 2 nitrates here and 2 hydrogens here, I need to put a 2 in front here. Lithium is a solid, and we react it with sulfuric acid, which is aqueous. That leads us to have lithium sulfate, which is 2 here, Aq here, plus H2 and G. And for this one, the only part we need to balance is the 2 in front of the lithium. Okay, just to finish ourselves off here, this is just the little trends that we can see in terms of metal reactivity. So potassium and sodium, they're from group 1. They are the most reactive metals you'll find, followed by the group 2 metals, calcium and magnesium, and then aluminium, zinc, and iron, which are more closer to your transition metals, while as the other transition metals like lead, copper, mercury are less reactive, and then silver and gold are non-reactive. So metals that are higher on this list are more reactive than the ones lower on this list. Heat is the most common way to make less reactive metals react. Some metals are so unreactive that they will not react under any conditions you do. Okay, so that's the key takeaway point there. Okay, so just a final question. I know I said that before, but this will be the final question of this lesson. We have steam trains that use coal to heat water in large boilers to produce steam needed to turn the wheels. Explain why it would be unwise to make these boilers out of iron. Now, if we actually have a look, it actually shows us iron is quite reactive to warm water, although it says dilute acid here. From the scenario we saw here, iron only reacts with steam to produce hydrogen gas and metal oxide. So if we use iron with the warm water, that's going to produce hydrogen gas, and obviously hydrogen gas is highly flammable, which if we're trying to use steam and fire to actually heat up the system, that can cause explosion. So we don't want that. Identify 2 metals that could be used to construct pipes for the transfer of dilute acids. If that's the case, we want to use something like copper, gold, or silver. So that's what we have here. And just to elaborate on, the container could rust as well due to that steam and also that hydrogen gas like we talked about before. Okay, so that concludes us for this lesson. We've gone through the reactions of oxygen, water, and dilute acids. In our next lesson, we're going to discuss the activity series for metals from increasing or decreasing orders. Thank you so much for listening up to this point. I will see you next time.